Hello everyone. Our next topic is about single line diagrams and impedance diagrams. Now first we have to consider the common symbols for our elements. So for example, an AC generator can be represented by a circle and we write G inside. And if we have a synchronous motor, again it is represented by a circle and we write M. So this may represent our synchronous motor. Now for the two windings transformers, we use this. This represents the windings on one side and the other windings on the other side. If we have a three winding power transformers, then our symbol would be three windings, with the middle winding here. And for auto transformers, when drawing single line diagrams, we can represent them as this one. The big circle here with this represents the primary and the secondary, whereas the small circle intersecting the bigger circle will be for our tertiary winding. And then for the power circuit breaker, as part of our network, will be represented by a square box. And then for our air circuit breakers, we have this symbol. And for the type of connections, we use this symbol delta for a delta connection, and we use Y for the Y connection, no, of our transformers. Now, if our transformer or generators is solidly grounded, and it is represented by this, and if it is resistance grounded, then the neutral is grounded through this resistor. And if it is impedance grounded, or for example, when we have a transformer used to ground our neutral, then we can represent that with an reactance towards the ground. And for current transformer, we represent it this way, while for potential transformers, we represent it this way. Now, a singular diagram can look like this, no, of a simple power system. We have here a bus. Well, actually, a bus is simply the part of the network where we make connections. No? For example, our generator 1 with its breaker is connected to this bus. And our generator 1 is reactance grounded. So we have this symbol, no, for the grounding of our generator 1. And we have another generator 2 also connected to this bus, and it is solidly grounded. So we have that. And then at this bus, we have a load connected, and we call this as load A. Now, some of the power generated by the two generators, that exists load, no? Because we have already load A here, so there can be exist load uh, generated by G1 and G2 that can be transported to other parts of the network. So we have here a transformer where the generator voltage, for example, if this is a 13.8, using transformer T1, which is YY connected and solidly grounded, and we have here circuit breakers both sides of the transformer windings. Okay, so this is step up to a higher value, let us say at 138 kV. Then we have transmission lines, going to the far side of the transmission line, where at the end we have another transformer 2 which is Y delta connected. Y is grounded on the high side and delta on the low voltage side. And transformer 2 is protected by these two breakers at both sides. Now we have here a bus where the low voltage side of transformer T2 is connected, and then to this bus we have another generator G3 connected to this bus with its power circuit breaker, and G3 is resistance grounded. And then at this bus also we have a load, uh, load B, okay, connected to this bus. So this is our single line diagram, okay, replacing our equipment like generators, okay, by their symbols, transformers, okay. For this is per phase, no? So we have, okay, two windings representing our three-phase transformer, because we consider here a per phase, a single line diagram, no? So single or one line diagram, okay, of our power network. Now, from the single line diagram that we had, okay, considered previously, we can draw the impedance, okay, diagram. Now this time we will replace our generators with their equivalent circuit or their models, no, for generators. So for generator 1, okay, we have generated voltage EA1, okay, plus or minus that polarity, and then we have its resistance R1 and reactance, synchronous reactance XS1. Now similarly for generator 2, we have generated voltage EA2 with the polarity positive here and negative, and then we have its small resistance R2 and its synchronous reactance XS2. Now these two generators are actually connected at the bus, no? And on the same bus, okay, we have also a load connected. So our load is just represented by an impedance, because with the voltage across these terminals and this impedance, so current can flow and power can be delivered, okay, to this load. Now, after that bus, okay, we have a transformer, no, that will transform, okay, the voltage on this side, okay, to a much higher voltage on the other side. Now, remembering the equivalent circuit of our, okay, power transformers, when we have magnetizing circuit considered, so we divided the total impedance of and we have the equivalent impedance of the transformer at both sides, and then we have the magnetizing circuit, no, for transformer 1. And then after the transformer, okay, we have transmission line, which is represented by its pi equivalent circuit. So we have here a total impedance of the line, and we have 1/2 of the admittance Y, and on the other side we have also 1/2 of the admittance Y. Now, and then after the transmission line, okay, we have the second transformer, okay, which has an equivalent circuit represented by this. Now, and then we have also magnetizing circuit, okay, to represent our transformer 2. And then to the terminals of our transformer 2 at the low voltage side, okay, we connect, okay, the load, second load, okay, C sub B. Okay, so this represents our load, and again, uh, through this impedance, okay, current flows and power is, okay, delivered to this load. And then another equipment connected to this bus is the third generator, where we have, okay, the second or the generated voltage EA3 with its resistance R3 and its synchronous reactance XS3. So this is, okay, the impedance diagram, and well, in this impedance diagram, we consider the magnetizing circuits of the transformers, okay, and the admittance of the transmission line. Now, as we have said before, that if we are going to consider the magnetizing circuit of our transformers, our analysis would be rather, okay, difficult. So, to simplify, okay, we just neglect, okay, the magnetizing circuit of our transformers. Okay, and then for the transmission lines, because the admittance is very small, okay, it's okay, effect on the sending end voltage and sending and receiving end current are not so much, no. So we can allow errors, small errors, okay, if we are going to neglect this admittance of, okay, the line. So what happens, then our impedance diagram can be simplified like this, no? So for the generator, we still have, okay, this equivalent, okay, circuit for generator 1, equivalent circuit for generator 2, and then our load is sub A. And then for transformer 1, okay, we can just get its equivalent impedance represented by RE1 plus JXE1. And then between transformer 1, okay, and transformer 2, we have, okay, the transmission line, okay, with its impedance R plus JX. And then, of course, at the end of the line, we have, okay, transformer 2 with the equivalent impedance ZE2, which is equal to RE2 plus JXE2. And then on this side, okay, of course, our second load is load B, you know, or represented by ZB, is still here, and our third generator is also uh, right here. So this is now our simplified, okay, impedance, okay, diagram.